be the first chair.
All right, thank you. So the first speaker today will be Jeff Murugan with on the quantum supremacy of SYK and operator growth on networks. Jeff, I will give you a 5-minute warning this time.
Thanks, Horatio. Let me just see if this works. Okay, can you see it?
Yeah, yes.
Cool. Great. Well, thank you, Horatio. Let me begin, like the other speakers, and thank Nathan and his team of organizers. I have some vague recollections of what it takes to put together something like Strings. And I must say, this year's meeting has been nothing short of spectacular, and we're not even halfway there yet. So I want to talk today about some work that I'm doing with, some work in progress with some really great collaborators, in particular, Jan Ole, who's a grad student at Autónoma Barcelona, Junho Kim, who's a postdoc at the Institute, Mateo Carrega at CNR Spin, and this project was really driven by Dario Rosa at the Institute for Basic Sciences in Seoul. It also builds on some earlier work by Dario and Mateo, as well as myself and a former student, John Gabriel Hartman, as well as John Schock. All right, so why SYK? Fortunately for me, Grisha Tarnopolsky and Steve Schenker did an excellent job of motivating the SYK model, which has really emerged as a mainstay of the field over the past few years, in part because of its versatility, and not just in high energy physics, but also in condensed matter theory, in many body particle, in many body physics, etc. And today I want to elaborate on yet one more application, if you want, of the SYK model, and that's the idea of quantum batteries. So this is a relatively new application of SYK physics, say, introduced by Dario Rosa and Mateo and their collaborators last year. And this work largely builds on that work and extends it in ways that I'll describe today. Okay, so the next question you might ask is, why batteries? So let me motivate a little bit why I'm thinking about batteries. Here's my country, South Africa. Each of those geotags that you're seeing there represents a town or a zone in the national power grid that doesn't have power. This is not cumulative counting. This is a day in the life, rather, circa February 2021. As our national power supplier institutes rolling blackouts to preserve the national grid. So if, like me, the word load shedding means something to you, it's part of your vocabulary, or let's say you lived through the Texan winter of 2021, then you're probably thinking about batteries too. Seriously though, quantum batteries are a novel idea to test some physics from quantum many-body physics, which may or may not shed some light on issues that we as a community of string theorists care about, like quantum gravity, black holes, etc. Okay, so let me start off then by defining what I'm going to mean by a quantum battery. We're really interested in studying small quantum systems. So a closed quantum battery is going to be, a quantum battery is going to be taken to be a closed, let's say, d-dimensional quantum system with some non-degenerate energy levels and some associated internal or battery Hamiltonian. Just to check, can you see the mouse moving around as well?
Yes.
Great. Okay. So what you see in the picture here is a two-level quantum battery that's spin down, which we'll take to be empty, and spin up, which we'll take to be a full battery, with some difference in the energy levels of, let's say, 2 epsilon, and we'll put this guy in a magnetic field that will be used later. The point here is that we're going to want to deposit and extract energy from the system by some set of cyclic unitary operations. The energy is extracted through some quench protocol, where we take the battery Hamiltonian and add to it some quench Hamiltonian, some quench potential, say, V of t, to give us a driving Hamiltonian. The system will evolve according to the von Neumann equations for the density matrix, which can be solved in terms of the initial condition, rho, and unitaries built from the time-ordered exponential of the driving Hamiltonian. And this, in principle, can correspond to any unitary transformation in the battery's Hilbert space. We're going to be interested in the work that's extracted from the system at some time tau, or work deposited into the system after some time tau, which is given by the difference between trace of rho h naught and the trace of rho of tau h naught. The maximal possible work that I can extract from the system is what's called the ergotropy of the system. Okay, so this is the maximum amount of extractable work optimized over the unitary operations. Okay. So amongst all the possible states of the system, we're going to call a passive state, or an empty battery, is one from which I can't extract any more work. And you can show that some state sigma is a passive state if and only if trace of sigma h naught is less than or equal to trace of sigma of t evolved by unitary operators u h naught. And this must be true for all unitaries u. So given this, any state, let's say rho, possesses a unique passive state, let's call it sigma rho, for which the work extracted, W max, is maximal. And the way we get that state, the way we connect rho to its passive state, is through some set of unitary operations that will rearrange the eigenvalues of rho in non-increasing order. The consequence of this is that the ergotropy, W max, is a bounded function. And this bounding of the ergotropy contains a canonical Gibbs state, omega beta, where beta bar, evaluated at the inverse temperature beta bar, where beta bar is the inverse temperature that's dialed so that the von Neumann entropy of the state rho, S of rho, is equal to S of omega beta bar. Okay. Interestingly, all thermal states are passive states, and specifically for a two-level battery, all passive states are thermal. Okay, but the product of passive states is not necessarily a passive state. This is going to be important in what's going to come, because we're going to try and build batteries from ensembles of batteries. So in particular, if I take some set of products of these unit cells, some set of products of passive states, while the product of passive states is not necessarily a passive state, a completely passive state is one which it is. So the product of sigma rhos is sigma of the product of rhos. Okay. The key point here is that a state is completely passive if and only if it's a thermal state. All right, so suppose we want to take we want to build a battery out of an ensemble of, let's say, n copies of this unit cell of d-dimensional batteries. All right, the global Hamiltonian that we'll construct will just be the sum over the individual cell Hamiltonians. And we're going to assume that the energy structure of each of the constituent cells is the same. Okay, if this is the case, then the question to ask is, can we extract any additional work from the product state until we reach a passive state? Right. The maximum amount of work per copy that we can extract from this quantum system is given by this W max. It's a function of n, goes like 1 over n times the trace of the product of rows minus the passive state corresponding to this times the n copies of the battery Hamiltonian. And for a large ensemble, you can show that the energy of the passive state doesn't differ much from an ensemble of Gibbs states. In particular, as n goes to infinity, this is tightly bound by, the trace of rho H01 minus the trace of omega beta bar H01. So there's a tight bound on just how much energy you can extract from this ensemble. The passive state that's associated to a product is diagonal in the eigenbases of the local Hamiltonian. And so it's a separable state. But in order to connect n products of n copies of this unit cell to its associated passive state, we're going to need at least two-body operations. And these two-body unitaries can be used to extract work from the system, and at every stage, keeping the state in a separable state, the system in a separable state. So optimal work can be extracted from the system without entanglement, but it requires longer times to do so. Okay. On the other hand, if we consider, instead of extracting work from the system, depositing energy into the system, then the deposited energy is simply the opposite of the work extracted. And as long as we're considering closed systems, which we will be in this talk, the two tasks are essentially equivalent. The problem here is that the unitary operations required to be performed on the system require a finite amount of time to be performed. This is a statement of the fact that the Hamiltonian is bounded, and so finite magnitude. So if I have a pure state, let's say psi, and I evolve psi to some other pure state phi by some unitary u that's generated by the driving Hamiltonian, then this time is bounded by this function t of, by this time t of psi and phi, which is given in terms of the distance between the two states in the Hilbert space and the minimum of the time averaged energy and the standard deviation of the driving Hamiltonian. From this, of course, the quantity of interest is going to be the power in the system. So the average power that I'm concerned with here is defined as the ratio between the energy deposited on the battery and the time required to perform the unitary operation. And the instantaneous power I get charging between, the instantaneous power of some unitary that's charging between the state rho and the evolved state rho of t is the time derivative of the work. And this is given by this expression, which importantly contains this commutator between the driving Hamiltonian and the density matrix. So what we want to do here is essentially compare two Hamiltonians. Two configurations of the battery, if you want. One configuration of the battery I get by basically just taking copies of the unit cell, so some local set of batteries in which when I drive the system with the driving Hamiltonian and I deposit energy into the system, I do so individually. And the second is that I can define I can link all the unit cells together to define some lowest energy state G, and some highest energy state E of global battery, in which case the energy deposited onto the battery after time evolution from G to E is just the n times the difference in the associated eigenvalues. So we want to consider the effect of some local driving Hamiltonian versus some global driving Hamiltonian, subject to the constraint that I really only have so much energy to deposit into the system. Here, I'm taking the operator norm, which gives me, which is the largest singular value of H. And since H is a Hermitian operator, this is the same as the largest eigenvalue. And I require that this thing be positive. The result of this is that the collective Hamiltonian that drives G directly to E does so along the shortest path in the space of entangled states, and gives a power advantage n times that of the local Hamiltonian H parallel. So I get a power advantage by coupling all of the unit cells together that I don't get by charging each of the individual cells by themselves. So one way of quantifying this advantage, and in particular the advantage of global driving versus local driving, is through this parameter that is the ratio of the average power of whatever driving process I'm using to the average power of using the local Hamiltonians. And this is the quantity called the quantum advantage, and it characterizes the power of these operations. This guy is typically bounded, and the bounds on it obtain from the kind of constraints that I put on the Hamiltonian. What's going to be important for us as we get to the SYK system is that for a k-local Hamiltonian with k bound k lying between 2 and n, and each unit cell participating in at most m interactions, gamma, the quantum advantage, is bounded by essentially the order of interactions. Specifically, the charging power can't be enhanced if I increase the number of unit cells in the battery, but the order of interactions between the unit cells is an effective resource in this game. Because we're talking about power, if I want to deposit large amounts of power into the system, deposit large amounts of energy over short times, this will necessarily, essentially a statement of the energy-time uncertainty relations, result in large fluctuations in energy, and therefore charging inaccuracies as well as instabilities in the system. One way to overcome these is to consider some system like, let's say, a quantum battery built out of harmonic oscillators in the Gibbs state that are charged through unitary operations. And if I use Gaussian unitary operations like single mode squeezing or combinations of squeezing and displacements, then these are operations that are preserved in the space of such unitaries, and I can essentially mitigate performance against optimization in the system. Another way to do it that's more interesting for us is to build the system using the SYK Hamiltonian. So here, again, let me just remind you that the Syk Model is just a quantum mechanical system of n Majoranas with all-to-all random Q-body interactions. And that has some rather interesting properties. The property that's most interesting for us is that it is solvable with Gaussian random couplings. The rest, while interesting from the perspective of the dual physics, is not going to play too much of a role in what I have to say today. What I want to do with this SYK Hamiltonian is to use it in a charging protocol. So the charging protocol that we're going to be using is to have some battery Hamiltonian quenched by the SYK Hamiltonian. So this is the driving Hamiltonian that we're going to consider. Lambda of t is a function that's 0 between when t is less than 0 or t greater than tau, and it's 1 everywhere in between those two. The stored energy in the system grows until some model-dependent, that is to say, what I choose for the quench Hamiltonian, until some model-dependent time scale, say tau star. Then it fluctuates wildly above some average value, E bar, with some model-dependent relative size between the highest energy and the lowest energy level. And this is for a local battery Hamiltonian H0. Okay. What we really want to do here is to compare these SYK batteries that are being driven with an SYK quench Hamiltonian to other models. And one way to make this comparison is to compare the optimal average power, which is a bounded function depending on these two variances. For
you have 5 minutes, Jeff.
Cool. For H0 and H1, where delta H1 squared corresponds to the charging speed, and delta H0 squared corresponds to the distance traveled in the Hilbert space. Essentially, the quantum advantage in the system corresponds to, sorry, this is ironic, but my battery is about to die. Let me just let me just adjust that. The quantum advantage corresponds to faster than linear scaling of P of n with n. The genuine quantum advantage, which I'm happy to discuss in more detail later, corresponds to superlinear n scaling of just this term delta of H0 squared, and not the quench Hamiltonian. Okay, so that's what we need to look for to detect a quantum advantage in the system. And in fact, let me go back to this picture. Here's the same energy depositing of the SYK model compared to the SYK battery compared to the many-body battery. And you can see that the difference is quite remarkable. The many-body quantum battery, something like a J1, J2 system, outperforms the spin chain battery significantly, but it still has significant energy fluctuations at early times. The SYK battery does remarkably better. It's got greater precision and stability at all times. It also saturates a larger and faster charge than other batteries. Okay, let me not talk about this here. So what we want to do here is ask how a change of interactions of the quantum system affects the quantum battery properties. So I'm going to talk about the idea of using graph theoretic language, where the SYK model corresponds to a complete hypergraph, and generalize that from a complete hypergraph to a general connected hypergraph. The only thing that changes here is the average value of the Gaussian random couplings includes a factor of the number of edges in the system. And here I want to consider two graph topologies, a circle topology and a star topology. Here, each Majorana is connected with its nearest neighbors, and here a single Majorana, psi n, say, is connected with all the others. In both cases, I'm going to pick the number of edges equal to the number of vertices equal to n, and compute the power, as well as this variance delta H0 squared. And what's remarkable here is that the star graph X model, where the H0 contains just a single Pauli operator, sigma x, outperforms even the standard SYK and SYK quantum batteries. So there's SYK4, here's SYK2, here's the circle graph, which is really horrible as a battery, and here's the star graph. Okay. So let me just say a few words about some analytic approximations to how to compute this power. Essentially, to compute the power, we want to calculate this quantity here, where the overline bar is an average computed over the Gaussian couplings. The fact that I'm averaging over the Gaussian couplings simplifies this commutator quite significantly, but nevertheless still results in a whole slew of nested commutators. And in practice, computing these proliferated nested commutators is quite formidable. But we can do it up to 8 nested commutators, and we get an expression for P8 bar. And we can check this P8 bar against the exact numerical computation. And you see that right up to the maximal charging power, they agree quite well, with significant deviations between the approximation coming from computing these nested Hamiltonians, nested commutators, coming only at late times. Okay, so let me skip this, and I want to talk about a class of particular networks or graphs that I want to put on this SYK model onto. The class is called a small world network, and the small world network is really where we're all sitting in our individual homes and not sitting on in Sao Paulo sipping caipirinhas. This is the small world network that represents flight paths through the world, and really the driver of the virus that we're dealing with at the moment. What we did was to put these quantum batteries on such a small world network, and the key point about the small world network is that it's a network in which there's a large number of cliques or neighborhoods, and a small number of interactions that stem throughout the entire neighborhood. So think about countries and people on international flights that can go across the entire world. The idea here is that you have a small path length in the network and a large amount of clustering. What we did was to calculate a quantity called the Krillov complexity, which will tell us how batteries on these networks compare to typical SYK type batteries. And this is really remarkable. So the main point I want to mention is that for small operators, the SYK2 model, so these are two Majorana fermions, or n Majorana fermions, or two-body interactions, perform significantly better than these small world graphs that are nearly regular graphs. And this corresponds to the fact that this corresponds to the fact that the SYK2 model is not really a scrambling system. We know that already. However, when I probe the system with large operators, so when my initial Hamiltonian H0 is a large operator with many Majoranas, say, then the situation is really quite different. And a highly connected graph like SYK2 actually does the job of spreading those operators through the network really well. If, on the other hand, I consider a small world network that's nearly random, then so a large number of long-range interactions, then the small world graph works just as well as something like SYK2. This is interesting because such a small world network has far fewer edges than the SYK2 model. So 2n edges versus n squared edges. But the interactions between the vertices in the system, the interactions between the Majoranas, is really quite efficient, enabling the system to spread the original operator out quite far. So let me conclude then with some observations and some open questions. The first is that quantum batteries provide yet another arena to display the power of the SYK model. I'm aware of the pun, and I don't apologize for it. Quantum advantage, this gamma property that we noted, really requires two ingredients. One is sufficiently non-local operators, the H0 that we started off with, and the other is interactions that are able to utilize the non-locality. SYK-like models on graphs provide a versatile set of quantum systems in which we can probe things like thermalization, localization, transitions between integrability and chaos, specifically in the small world model. And for this, I refer you to the work of Xu and Susskind and Swingle, and Garcia, Rosa, Fabalscott, etc., as well as a large body of work by Andy Lucas, and our work with Jean-Gabriel Hoffman and John Schock. And then let me finish with some open questions. The first open question is a very technical one that I didn't get to cover much, but essentially the question is, how tight is this bound on the power of charging power? And consequently, how tight is the bound of the quantum advantage for quantum batteries that are not just defined on a regular lattice, but on general graphs. So Dario Rosa and his student have some work coming out that clarifies this. And then essentially, because of the statements that I made in terms of the Krillov complexity, operator complexity, I'd like to understand how these results relate to the operator thermalization hypothesis work of Shalom and Zahn and et al. From a couple of years ago. And then finally, given the audience in this meeting, it obviously begs the question, what are, if any, holographic interpretations of these statements? So let me finish by, again, thanking the organizers. And it's a wonderful statement of our community that every year, come hell or high water and pandemics and rain and shine, we get together to celebrate the birthdays of Douglas Stanford and Christian Jensen, who is our next speaker. I was one of the next speakers who celebrates his birthday today. So I'm glad that the organizers were able to put together such a wonderful birthday conference, and thank you very much for your attention.
Thank you, Jeff. Let's thank him. So we are a little bit over time, but let's have some questions. Well, I see one in the chat, actually, maybe several. So let's see. So the first question was, what happened when you consider a quantum battery is attached to a thermal bath and taking energy out of that, like open quantum system?
Right. So I don't know is the answer. It's a really interesting problem that we're still thinking about.
All right. Let's see. There was another question from Chris Krillova. Does it matter if the graph is oriented or not?
Does it matter if the graph is oriented or not? By oriented, do you mean if I label the edges in some way?
I think so, yeah.
With, let's say, arrows. Yes, I would imagine yes. And you know, one way to think about this is the difference between, let's say, real Majoranas and complex Majoranas in the SYK versus charge versus complex SYK case. So yes, the algebraic graph properties change in that case, and I would imagine that there would be some change, but I haven't really given much thought to it.
So would that just be a specific case if it's oriented? Could you extend it to non-oriented and see what happens?
I'm not sure, to be honest.
Okay. Great.
It's an interesting question.
All right, so I think we're a bit over time, unfortunately. So let's thank Jeff again. All right.